Let us look at proposition number 3132 of works of Archimedes, specifically from on conoids and spheroids. The proposition says, if a plane divides a spheroid into two unequal segments, and if AN and A prime N be the axis of the lesser and greater segments, respectively, while C is the center of the spheroid, then greater segment is to the cone or segment of the cone with same base and axis is equal to CA plus AN is to AN. So let's do a little bit of construction. Take a plane through the center C and draw a plane perpendicular to this plane through C. So we get an ellipse of intersection. Now through C in this plane, we take a straight line, the major axis or axis, let's say A prime. Now let's take a point N and let's draw a plane perpendicular to this plane and this plane through N, so that we have a line of intersection, let's say P prime. Similarly, we draw a plane through C parallel to this plane, so that again we have a line of intersection, and let's say these are B and P prime. So here segment AP P prime is the minor segment and A prime P prime segment is the major segment. This is the intersection, a circle of intersection between the spheroid and the plane passing through P prime. And similarly, this is a circle of intersection between the spheroid and the plane passing through B prime. Here we can visualize these cones. This is AP P prime cone, and this is the cone AB prime. Again we have another cone A prime P prime. Now the proposition is talking of CA plus AN. So CA plus AN, we want it one single straight line. So let's say we take CA and the same length we mark out here. So let's say H. So we have taken H such that HA is equal to AC. So that means CA can be substituted with AH. So we end up with AH plus AN. AH plus AN, which is nothing but NH. So our ratio becomes NH is to AN. Okay. So similarly on this side also, let's mark a point H prime, so that A prime H prime is equal to CA prime. Now, half the spheroid is double the cone ABB prime. We have seen this in the previous proposition, which means the spheroid is equal to 4 times the cone ABB prime. So, cone ABB prime is to cone APP prime is equal to the ratio AC is to AN compounded with the ratio BC square is to PN square. AC and AN are the axes of these cones and BC and PN are the radii of the base of these cones. Okay, now let's look at this. Cone ABB prime is to APP prime is equal to AC is to AN times, now BC square is equal to AC times CA prime or A prime C, and PN square is equal to AN times A prime N. So we substitute this. So we end up with AC is to AN times AC times AC prime is to AN times A prime N. Now let's take AK along A prime such that AK is to AC is equal to AC is to AN. So what does this mean? We are taking AK such that AC is the mean proportional between AK and AN. So let's take K. So this is the point K. So AK is to AC is equal to AC is to AN. Let us simplify this diagram a little bit to make it more readable. Okay, and just to be able to visualize it, let's draw these lines. AK is to AC. Let's multiply both the antecedent and the consequent by A prime N. We get AK times A prime N is to AC times A prime N is equal to AC is to AN. So that our statement here becomes cone ABB prime is to cone APP prime is equal to AC is to AN is this. So we substitute AK times A prime N is to AC times A prime N times AC times AC prime is to AN times A prime N. And if we simplify this, because cancellations will happen, we will end up with AK times A prime C is to AN times A prime N. Now let's take cone APP prime is to segment APP prime. That will be equal to A prime N is to NH prime. Again, previous proposition. Now we multiply both the antecedent and the consequent by AN. So we end up with AN times A prime N is to AN times NH prime. Now, here if you notice, we have AN times A prime N is to AK times A prime C. So we substitute it. AK times A prime C is to AN times NH prime. Now, how did we get this? It's not just simple substitution. Look at it. Cone ABB prime is to cone APP prime. Here, cone APP prime is to segment APP prime. So that means X equally, what we end up with is AK times A prime C is to AN times NH prime. Okay. Now, let's look at spheroid is to segment APP prime. Now, say here the spheroid is 4 times cone ABB prime. And cone ABB prime is AK times A prime C is to AN times A prime N, that is with respect to cone APP prime. But we are interested only in cone ABB prime. So we take 4 times A prime C. 4 times A prime C is HH prime. So HH prime times AK is to AN times NH prime. Segment A prime PP prime is to segment APP prime is equal to HH prime times AK minus AN times NH prime is to AN times NH prime. So think of it like this. Spheroid, we have segment APP prime. If we subtract these two, we get segment A prime PP prime. So subtraction involves what? Spheroid is HH prime times AK minus segment APP prime is AN times NH prime is to AN times NH prime. If we work it out, we end up with AK times NH plus NH prime times NK is to AN times NH prime. Now, this might be a little bit confusing. So let's look at the workings of this. So here, see here, this is what we had. Segment A prime PP prime is to segment APP prime is equal to HH prime times AK minus AN times NH prime is to AN times NH prime. Now, how did this arrive? How did we arrive at this? Let spheroid equal to S. Segment A prime PP prime be X and segment APP prime be Y. So ratios I'm writing in this form. Spheroid is to segment APP prime is equal to HH prime times AK is to AN times NH prime. Now, remember, X is nothing but S minus Y, right? And S is equal to Y times this. So if we do that, Y will be there common. So we take it out and we write it as Y times HH prime times AK by N times NH prime minus 1. And we work it out. LCM of the denominators. And as we work it out, we get HH prime times AK minus AN times NH prime by AN times NH prime. Now let's take it to the next step where we arrive at this. So HH prime can be written as HN plus NH prime. So here HH prime we substitute with HN plus NH prime times AK minus AN times NH prime. Again we start working it out. We distribute, we get HN times AK plus NH prime times AK minus AN times NH prime is to AN times NH prime. Now here NH prime is common to both, so we take it out. NH prime times AK minus AN. Now AK minus AN is what? AK minus AN is NK. So we have ended up with HN times AK plus NH prime times NK by AN times NH prime, which is what we had arrived at. AK times NH plus NH prime times NK is to AN times NH prime. Okay, now that point is clear, let's proceed. Now let's take segment APP prime is to cone APP prime is equal to NH prime is to A prime N. So here it was cone APP prime is to segment. We have just taken the reciprocal of that, both sides. Now NH prime is to A prime N. We multiply both the antecedent and the consequent by AN. Now cone APP prime is to cone A prime PP prime is equal to AN times A prime N. Let's take AN times A prime N is to A prime N times A prime N. What have we done? We have taken this ratio and we have multiplied both the antecedent and the consequent by A prime N, so that we end up with AN times A prime N is to A prime N times A prime N, which becomes A prime N square. Now segment A prime PP prime is to cone A prime PP prime is equal to segment A prime PP prime is AK times NH plus NH prime times NK, and cone A prime PP prime is A prime N square. So basically we are combining these proportions. A prime N square can be written as AC square plus NH prime times CN. Now how do we arrive at that? See here, this is A prime N square, A prime N square, that we are decomposing into this as square and rectangles. So this is A prime C square. Now this is a square on A prime C, but remember A prime C is equal to AC. So this is AC square. On completing this figure, we end up with a gnomon which is equal to NH prime times Cn. So that we can say now A prime N square is equal to A prime C square or AC square plus the gnomon NH prime times Cn. Now AC square is what is equal to AK times An. How? Because remember here, if we take the product of the extremes equal to product of the means, we get AC square is equal to AK times An, right? So which is what we have done, AK times An plus NH prime times Cn. But AK times NH is to AK times AN. Here if you notice, in both the antecedent and the consequent we have AK as one of the factors. So they can be taken out, removed. So we end up with NH is to AN. Now NH can be written as what? NH can be written as AC plus AN. Why? Because AH is equal to AC, which is what we had to prove. But we need to go a few more steps because we have shown that these two have this ratio. We have to take care of these two as well. To be able to say segment A prime P P prime is to cone A prime P P prime is in this ratio using this itself. So let's do that. AC plus AN is to AN can be written as AK plus AC is to AC. Now, how did this come? Now, here AC is to AN is equal to AK is to AC. So, AC can be substituted with AK and AN can be substituted with AC. So, which is what we have done. Now, AK plus AC is what? AK plus AC. AC is nothing but AH. So HK is to AC. Now again, if you notice, NH is to AN is equal to HK is to AC. These ratios are same. So which means we can write it as HK minus NH is to AC minus AN. HK minus NH. HK minus NH gives us NK. And AC minus AN gives us CN. So this ratio becomes NK is to CN. And we can multiply both the consequent and the antecedent by NH prime to end up with NH prime times NK is to NH prime times CN, which is exactly what we have. NH prime times NK and NH prime times CN. So, which means we have arrived at the correct conclusion. That is AK times NH is to AK times AN is equal to NH times AN, which means segment A prime PP prime is to cone A prime PP prime is equal to NH is to AN, which is equal to CA plus AN is to AN. Segment A prime PP prime is to cone A prime PP prime. That was proposition 31 and 32. And most importantly, the last proposition of on conoids and spheroids. Again, let me remind you, there is a link to a PDF book which describes all these propositions in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now. Bye.